Now here we are starting with the conformational isomerism. They are also termed as rotamers, conformers or rotamers. Now in this case, it is a part of stereoisomerism where there is a free rotation along the carbon-carbon sigma bond. Due to free rotation, we get several different possible orientations and they all are termed as conformations. They all are termed as conformations, or we can say they are conformers or rotamers. They are not true isomers. Why they are not true isomers? Because they are continuously interconverting into each other, or we can say they are not true isomers because they are interconvertible. That is why conformational isomers are non-isolable, whereas configurational isomers are isolable. We can separate them also. So here we are talking about firstly Newmann projection. In Newmann projection, suppose this is carbon number 1, carbon number 2. This carbon is connected with 3 atoms, that is A. Suppose we can write here hydrogen also, and second carbon B, second carbon is connected to B. 3 B atoms are there. Now in this case, when we write it, we write its Newmann projection like this. Front carbon, this is this one. Front carbon is this one. Back carbon is not visible because in Newmann projection we write it in that manner that front carbon is visible. Like these are the 2 carbons. Carbon number 2, carbon number 1. When we write it in Newmann projection, it is like this. Now, yes, now you can see the back carbon is not visible, but front carbon is visible. That is the front carbon 1. Back carbon is not visible, that is the back view. It is the front view. When we combine them, we get Newmann projection. So this is one such projection. Front carbon 1, 3 groups A. Back carbon, it is understood that behind this one more carbon is there, which is C2, which is not visible. So we mention it like this, and it is connected with 3 other groups, 3 B atoms. Now this angle is dihedral angle between A, C1, C2 and B. This is phi, which is dihedral angle. Okay. Then there are different forms in Newmann projection. One is eclipsed form. Eclipsed form means the dihedral angle can be 0, 120, 240 and 360. These dihedral angles will result into which form? Eclipsed form. Now here example I have taken in which front carbon A, 2 hydrogens are there, back carbon B, 2 hydrogens are there, and A is exactly in front of B. So it is which form? It is fully eclipsed form. Why fully term I am using? Because there are other possibilities also where A is not in front of the group B, because hydrogen will be the smallest possibility. Any other group is present, then these 2 bulky groups are exactly in front of each other. They are exactly in front of each other. That means it is fully eclipsed form. When we rotate it, suppose by 120 degree, then B will be there. Again eclipsing takes place, but this time A, and there is in front of A there is hydrogen, and B in front of B there is small group which is hydrogen. So in eclipse form it is partially eclipsed. Similarly, next one, if we further rotate by 120, overall it becomes 240. B is there, A in front of H, B in front of H and H in front of H. It is again partially eclipsed form. If all the groups are same, suppose all are hydrogens, then we can use only eclipsed term. No mentioning of fully eclipsed or partially eclipsed. So this is about eclipsed form of Newmann. Now next is staggered form. In staggered form, the dihedral angle can be 60 degree, 180 degree and 300. Like in the first one, A and group B. Remaining atoms are HH. Between A and B, A, C1, C2 and B, the dihedral angle is 60 degree. When we rotate it exactly 300, it becomes this one. This is phi, that is 300 degree. In staggered form, if that is the arrangement, that is 60 degree between AB and or 300, it is termed as gauge conformation. in staggered. If all are same, suppose all are hydrogens, then we cannot use the term gauge or antiform. Then we simply say they are staggered. But if any arrangement is given and in staggered, then we have to say it is which form? Then it is gauge form. Another possibility, if A and B, they are exactly opposite, that is 180 degree. This is which form? It is antiform. It is antiform when two groups are exactly opposite to each other. So in staggered form, it is antiform. In staggered form, these two results into gauge conformation. Then third type is skew form. All conformations except staggered and eclipse, they are termed as skew forms. Phi not equal to all these bond angles will be skew conformations. Okay, then one more projection is there, which is Sawhorse projection. In this we show the bond between first carbon and second carbon as well. You can see here it is ethane molecule. Now in ethane molecule, front carbon and then hydrogen, second carbon also in front hydrogen, H in front of H. This hydrogen is also in front of other hydrogen and that hydrogen also in front of that. This is which form in Sawhorse? It is staggered form. Okay. Now if front carbon we rotate exactly by 60 degree, okay, or I say by 180 degree, they all look like similar. So in this case you can see that this hydrogen now, which was earlier above, suppose I am rotating 180 degree, this will be here, other hydrogen is exactly opposite. Clear? Then this hydrogen is in between these two, just like this is in between these two. This hydrogen is not here in front of other one. Why? Because it is rotated and now it is slightly like this, so it is in between them, and this is not exactly in front of each other. So this is which form? Sorry, this is staggered form, and now which I told by mistake, it is exactly in front of each other, it is eclipse form. So in Sawhorse, if the groups are exactly in front of each other, it is eclipse form. If they are rotated by which angle? By 60 degree, by 180 or by 300, they are simply termed as staggered form. Now some basic terms like conformers. Conformers means the infinite orientations. Conformers, other term is rotamers, the infinite orientations which arises due to free rotation, along carbon-carbon single bond free rotations. These infinite orientations are termed as conformers or rotamers, right? Then another term is configurational isomers. Then another term is conformational isomers. The isomers which are at the energy minima, are termed as conformational isomers. Now how energy minima? I'll explain it through example of ethane by drawing a curve. You understand it. The conformers which are at the energy minima, we will say these are conformational isomers. Then another term is conformational energy. It is the potential energy difference between the most stable conformer and least stable conformer. Between these two, the energy difference is termed as conformational energy, right? Then next term is van der Waals strain. Van der Waals strain means, suppose I am talking about this example. Okay, about this example, suppose I am substituting here two groups. Here I am putting group A, here I am putting group B. Now, in this case, which is eclipse form, A is exactly in front of B. H, although smaller, but they are in front of each other. So this is the strain which arises when the bulky groups are exactly in front of each other. That strain due to the bulkiness of the groups which arises is termed as van der Waals strain. Due to the bulkiness of the groups, the strain which is there, which is termed as van der Waals strain. Another is torsional strain. Torsional strain arises between the bond pair electrons. Like in this case, I'm talking about simply eclipse and staggered term. Maybe you can use Sawhorse or Newmann. So here in this eclipse form, the bond pair electrons are exactly in front of each other. So the repulsion between bond pair electron arises. This strain or this force of repulsion is termed as torsional strain, right? So when the groups are exactly in front of each other, their bond pair electrons are exactly repelling to the maximum. When we rotate it by 60 degree or by other degrees in staggered form, it minimizes. Why? Because bond pair electrons are not exactly in front of each other. Therefore, the torsional strain is maximum in eclipsed forms and minimum in staggered form. Like these are the staggered forms above. So AB, there may be van der Waals strain, AB van der Waals strain, AB van der Waals strain very less. Why? Because it is due to bulkiness of groups, but they all are staggered forms. So no bond pair electrons are in front of each other. So these are having least torsional strain. The strain that is due to the bond pair electrons is torsional strain, and that due to bulkiness of the groups is van der Waals strain. I hope you get these basic terms. Now next is conformational analysis of ethane. In conformational analysis of ethane, we can write several possibilities, but I am writing only two because other forms will be repeated. Like at phi 0, all the hydrogens are exactly in front of each other, that is phi 0. Now if you rotate by 60 degree, we get this type of conformation, which is phi 60 degree. Then you further rotate by 60 degree, it becomes exactly like first one, and that means overall 120 degree. Further rotate by 60 degree, it becomes total 180 degree and just look like 60 degree. So here other forms will be repeated of either eclipsed form or staggered form, other forms. So I am not writing again and again the similar forms. Here I am explaining it through the diagram, which is potential energy diagram, potential energy versus dihedral angle. When dihedral angle is 0, there is maximum torsional strain. Van der Waals strain will be negligible. Why? Because hydrogens are present, very small groups. But we know that at eclipsed form, torsional strain is maximum. So in this case, at 0, if this is the energy, at 60 degree it is stable, this is a staggered form. Then again high because of eclipse form 120. Then again 60 degree added, this is 180 degree. Again 60 degree rotate, it will go to 240 degree, and which is again maximum in the strain. Now they have same values of energy, all are having same values, all eclipse forms same energies, all staggered forms they have same energy. Why? Because all groups are same, that is hydrogen. Then further it becomes which one? It is 300 degree, and then finally again it is 360 degree. Now 12.5 is the energy gap here between the most stable and least stable form, that is between staggered and eclipse form for ethane. That value is given in NCERT. This is given 12.5 kilojoule per mole. Now in this case you have energy curve here. Now among them you have how many minimas? First, second and third. Now if you remember, I told that there are infinite orientations possible, but how many conformational isomers are there which are found at energy minima? That are 3 at 60 degree, at 180 degree and 300 degree. Then stability, here there is only two forms. Staggered form is more stable than eclipse form. Right, you can draw for more also, but in NCERT it is given for 2 carbons, so I am not going beyond that. Otherwise you can try for butane as well. Next question is that you have to find the identify the compounds from their Newmann projections given below. Now you can pause this video, you can try each and every example. This is given Newmann projection, write the normal structure of the molecule. Same way here, Newmann projection is given, write the normal structure, same way there. You can try, you can pause this video, try this question and check your answers. In the first one, front carbon is this one, back carbon is not visible. Now front carbon contains CH3 and how many hydrogens? 2. Back carbon contains 2 hydrogens and 1 methyl. So as per this, these are the 2 carbons. First carbon this one, second carbon this one, as per the Newmann projection. Second example, first carbon. First carbon contains hydrogen CHO and CH2OH. CHO, CH2OH. It is first carbon as per Newmann here. Newmann front carbon it is. Back carbon is carbon with CH3 and OH and COOH. That is the, I am marking 1, 2 as per the front carbon 1, back carbon 2. Third one, in third one, front carbon 2 hydrogen 1 OH, back carbon 2 hydrogen 1 OH. This is glycol, ethylene glycol. Now next is one particular concept which is intra-hydrogen bonding or intramolecular H bonding in case of Newmann projections. Like example is, we have this arrangement, carbon which contains OH and another group Z, that Z can be OH also. Here we do very specific examples. It is not we are doing with several examples, because the point is that due to intramolecular H bonding some extra stabilization takes place and that can be shown in the stability order. That is the only point. Okay, so Z can be OH, NH2, fluorine, CHO, NO2, carboxylic group, COO group. Now here, if we take both OH, carbon 1, carbon 2, we can write several possibilities of staggered form and eclipse forms, like 0 degree, 120, then 240 and then 360. But I am not writing these forms right now. I am only writing the staggered forms. One form which is 60 degree and OH group, which are here. This is in staggered, it is gauge form. In staggered, it is anti form. Now generally you know that the stability order, if we take butane or normal carbon chain, stability order is staggered more stable than eclipse. If different staggered forms are there, in staggered form generally anti form most stable. Generally, again I am saying generally stability anti most stable, then comes gauge form, then comes partially eclipsed form, and least stable is fully eclipsed form. It is general stability order. But due to a special case of intramolecular H bonding, there is some stabilization takes place, and which I am explaining here, that due to intra H bonding in gauge form, this gauge form is more stable than its anti form. Otherwise, generally due to bulky groups are exactly at maximum distance, van der Waals strain very less, and generally anti form stable. But in this case of intra H bonding, gauge form is most stable. Then comes here which form? Anti form. Now between partially eclipsed and fully eclipsed, partially eclipsed is more stable as compared to fully eclipsed form. Why? Because in partially eclipsed at least same groups are not in front of each other, like 2 OH groups are there exactly in front of each other, then it is fully eclipsed form. So there will be more van der Waals strain. So this is a stability order here due to H bonding. Otherwise general stability order is anti form, gauge form, partially eclipsed, and then fully eclipsed form. Clear? You can take other examples also. You can put there NH2, you can put there fluorine, you can put there CHO. Now next is one question. Write down the most stable conformer of this molecule. Now you can pause this video, write it down in your notebook and then check the answer. Now in this case we can mark this carbon as 1, 2, means front carbon 1, back carbon, which is with NO2. Now in this case front carbon contains OH and 2 hydrogens, back carbon contains HH and 1 NO2. Now we know that NO2 can also participate in the H bonding with, it can also participate in H bonding with the hydrogen of oxygen, and therefore the most stable form will be gauge form, not anti form. If H bonding factor is not there, then anti form will be more stable. Then next is the conformations of cyclohexane. Now in cyclohexane we have these conformations. First is chair form. This is a chair form. Second is twist boat. Twist boat form. Third is boat form. Fourth is half chair. It is only for the information you can use, otherwise as per NEET chances are very less that much details are useful. Otherwise simple point is there. These are the conformations of cyclohexane. Among them the most stable is chair form, then twist boat, then boat, and least stable is half chair form. One more information is there, that twist boat is the only form which is optically active. Twist boat is the only form which is optically active among these 4 conformations of cyclohexane. Now next is one question which is important to make better understanding of conversion of the conformational structures into Fisher projection. So that question will give you much better idea. By solving this question you understand how to convert from Newmann to Fisher or Sawhorse to Fisher, or how to compare if any question is given that find out the relation between the given isomers, and if the given isomers are in Sawhorse or Fisher project or Newmann projections. Okay, so the question is, we have these structures M and O, P, Q. These are the molecules given in their conformational isomers. One is given in Sawhorse projection, one is given in Newmann projections. Now you have to find what is the relation between the structure M and N. Then you have to find the relation between structure M and O. Then find relation between M and P, and find relation between M and Q. So how to approach this question? Whenever any Newmann projections are given or Sawhorse projection, always try to write them in Fisher projection. Convert them into Fisher projection. And how you will convert? Remember that eclipsed form of Newmann, eclipsed form where each group is exactly in front of each other, it is also just like Fisher projection. Why? In Fisher projection also what we write? We write each group in front of each other. So whatever projection is given, try to convert it into eclipsed form, and from this eclipsed form whichever groups are in front of each other, put them as it is in Fisher projection. Okay, so we can say the term that eclipsed form is basically a Newmann, basically a eclipsed form is basically a Fisher projection. Maybe here eclipsed form of Newmann, here eclipsed form of Sawhorse projection. Clear? So you firstly copy this question and then understand that you have to find this relation between M and N, M and O, M and P, M and Q. Try this question, pause this video and then check your answers. Like which are diastereomers, which are enantiomers. If they are identical also, then find which are identical. I am giving you hints. Now these are the structures of the following molecules starting with M. In case of M, it is eclipse form already, and Fisher projection, and Fisher projection represents eclipsed form of Newmann or eclipsed form of Sawhorse. Fisher projection represents eclipsed form of Newmann or eclipsed form of Sawhorse. So here, if Cl in front of CH3, H on the right side, H on the right side, OH on the left, OH on the left. Now you can write it here. Cl, CH3, H, left side OH, H, left side OH. This is the structure of M. Similarly here, already it is eclipsed form, and we know that Fisher projection is eclipsed form of Newmann or Sawhorse. So CH3 in front of CH3, then H on the right with respect to CH3 and OH on the left. CH3, H, OH, then other group you can easily write in front of H, OH is there, H. Now here Cl above, Cl below, what we can do, we can easily rotate it in the plane of paper, then this will exactly look like this from vertical part, Cl, CH3, but there is no use of rotating because OH, OH are opposite side. So these two are stereoisomers, but they are not mirror image of each other. So M and N, they are diastereomers with respect to each other, because you can easily see here both OH on the same side, here both OH opposite. Now next is O. In case of O, we can convert this molecule into which one? From staggered to eclipsed form, just like we have structure M. And how we can convert? We rotate the molecule exactly 180 degree, because Cl and CH3, they are exactly opposite given. Done. So when you rotate this molecule, Cl exactly below, H on the right side, OH on the left, you can get this one, Cl and CH3, exactly H on the right, OH on the left, same representation like this one. So we can say these two structures, they are what? They are identical structures. M and O are identical. How you can cross check? If you remember, if for this chiral center both having same chiral carbon, means chiral carbon and ClOH, ClOH and this group, find out RS, and when you get same configuration, that means they are identical. If you get opposite configuration, they are enantiomer. So here you will definitely get same configuration, therefore M and O are identical compounds, they are same compounds. Then P. Now P is given in Newmann, and Newmann which given? Staggered given. So we convert this Newmann into staggered form, Newmann staggered form into eclipsed form by rotating it with 180 degree and simply converting it into same format. Just like here, if I rotate it by exactly 180 degree, it is CH3Cl. Then on the right side we have which group? OH, OH and H. Now this is the form. Now when you write it, both CH3Cl, Cl, CH3, OH on the right side, H on the left. Now this molecule and M, they are exactly mirror image of each other and non-superimposable. Therefore M and P, they are enantiomers. And how you can cross check it? You can cross check simply by finding RS also if you want. Otherwise you can easily see P and M, they are mirror image, whereas O and M, they are not mirror image, they are exactly identical. And we can confirm it also by RS configuration. The important part is we should convert the given Sawhorse or Newmann projections rightly into Fisher. And how we are converting? We are converting the given Sawhorse projection into its eclipsed form first, and Fisher projection is basically eclipsed form of Sawhorse or eclipsed form of Newmann, right? Then next, in Q structure, again we rotate exactly by 180 degree and CH3Cl like this, and then H in front of OH, H in front of OH. That means this type of structure is formed, and then you can easily say that both OH groups are opposite. So definitely Q and M, they are undoubtedly what? They are diastereomers, because they are not mirror image of each other. So M and N, they are diastereomers. M and O, they are identical. M and P, they are enantiomers, and M and Q, they are diastereomers. Okay.